Okay, so welcome back to this next video in which we are discussing the epidermis. Okay, right. So we have now discussed the basic structure of the skin, and we've seen where the epidermis fits into the bigger picture of the skin. Okay, we've then said that the bottommost layer of the epidermis is going to consist of this basement membrane, which is made up of these two separate layers, lamina densa, which is closer to the dermis, and then lamina lucida, which sits above lamina densa and is closer to the epidermis, and in fact is the layer which the basal keratinocytes, which is this bottommost layer of cells of the epidermis, are actually attached to. Okay, right, so we now want to discuss the structure of this lamina lucida of basement membranes. Okay, now this is going to involve the study of proteins known as laminins, because these are the key components of the lamina lucida. Okay, now laminins are heterotrimeric proteins. They are made up of 3 separate subunits joined together. Now, the 3 separate subunits that they are made up of are known as the alpha subunit, the beta subunit, and the gamma subunit, or the alpha laminin, the beta laminin, and the gamma laminin. And together they make a heterotrimeric laminin, or a laminin heterotrimer. Okay, right. So let me now show you the structure of one of these heterotrimeric laminins then. Okay, so we'll start off just by discussing the structure of an alpha laminin, and then we'll see how we're going to join it with a beta and a gamma laminin. Okay, right. So the alpha laminin then is a single polypeptide, so here is its amino terminus. Okay, then an important domain that it has at its amino terminus is known as the laminin N-terminal domain. Okay, now this domain is going to become extremely important in a moment. This is actually going to be involved in the polymerization of these laminin proteins. And this polymerization is going to be very important for the structure of the lamina lucida. Okay, so this is what's known as the laminin, okay, and then it's the laminin N-terminal domain. Okay, now for short, the laminin N-terminal domain is often just abbreviated to the LN domain. Okay, so you abbreviate laminin and then N-terminal just down to LN basically. So laminin is reduced to L, and then N-terminal just to N. So this is called an LN domain. Okay, and this is the LN domain of the alpha subunit of our laminin heterotrimer. Okay, then after the LN domain, what you then have is a very long alpha helical portion. Okay, right. I'm not actually going to draw this as an alpha helix. Okay, I'm just going to draw it as a straight line, and you'll see why I do this in a moment, because it will make it much easier to show the heterotrimer. But this region is actually an alpha helix. Now, before we go on, I would like to discuss something about alpha helices with you, which is going to become extremely important. This is going to show up everywhere, basically, in our discussion of the epidermis. Okay, so let's just go over the page and discuss something very important about alpha helices. Okay, right. So firstly, let me just make sure that everyone is familiar with what an alpha helix actually is. So basically, an alpha helix is a secondary protein structure, okay, which just means that it is held together by interactions between the functional groups in the peptide links of the polypeptide. Okay, right. Now, an alpha helix actually looks like a spring, basically. So it's got this spring-like structure. So at the moment, here is our beginning, okay, and then you're working your way back to the back of the page. So I'm going into the page, now I'm coming back out of the page, I'm looping out towards you, okay, and now I'm turning back around, I'm going into the page, okay, and then I'm looping back out of the page towards you, round and round in a spring-like structure like so. So this is what an alpha helix actually looks like. Now, let me just discuss how they're actually held together then. Okay, so basically they're held together by interactions between functional groups in the peptide link. So this line, this actually represents a polymer of amino acids. So this represents amino acid after amino acid, and now I'm suddenly going to actually draw one of these amino acids out. Okay, so let's go for this. So here's the amino group here. Whoops, what am I doing? Not like that. Okay, here is a hydrogen coming off that nitrogen atom. Okay, then off the nitrogen we have our alpha carbon, which will have a hydrogen coming off like so. Okay, then we've got our R group here. Then we've got our carboxylic acid group here. Okay, so that is an amino acid residue within this protein. Now what's going to happen is the polypeptide is going to go back to being represented just as a line. Okay, then now it's looped back into the page, and now it's coming out towards us again, and now I'm going to show the next amino acid. Okay, so I'm going to, well, the next one that I actually want to draw. Okay, there are loads in between here. Okay, then we've got an amino group here. Okay, an alpha carbon here, and then we'll have to sort of draw it looping back now. Here's the carboxylic acid group. Here's the alpha carbon's hydrogen, and here's the R group, which doesn't necessarily have to be the same as that one, so I'll put an R prime here. And then the polypeptide will continue. Okay, so what I now want to show you is how these two amino acids are actually going to bind together. Now, it's not going to involve the R groups. That's what the important thing to understand in secondary protein structures. Okay, secondary protein structures are not held together by interactions between the R groups of amino acids. They are held together by interactions between the amino groups and the carboxylic acid groups. You're only allowed to use these groups, basically, of the amino acids. You're not allowed to use the R groups here. Okay, tertiary protein structures involve interactions between the R groups. Secondary protein structures involve functional groups within the peptide links, and the functional groups within the peptide links are this amino group here and this carboxylic acid group here. Okay, right. So basically this amino group here is going to form a hydrogen bond with this carboxylic acid group here. Okay, now to understand hydrogen bonding, you need to have a good understanding of what electronegativity means. Okay, so let's firstly discuss electronegativity. Okay, so basically let us study this bond between a nitrogen atom and a hydrogen atom as a good example. Okay, so this is a single covalent bond between the nitrogen and the hydrogen atom. Okay, so it's going to have two electrons within it, one that has come from the nitrogen and one that has come from the hydrogen. Okay, so let's say that this one that I'm colouring in red here, this came from the nitrogen here. Okay, and this one that I'm colouring in blue here, this came from the hydrogen here. Okay, now, these two electrons are sitting nicely between the nitrogen and the hydrogen. The question then is, are they sitting directly in the middle? Okay, i.e., are they right in the middle between the nitrogen atom and the hydrogen atom, or are they slanted to one side? Okay, now, to answer that question, we need to be thinking about what forces are these two electrons here actually going to be feeling. Well, they're going to be feeling attraction towards the nuclei of both the nitrogen atom and the hydrogen atom. Now, the question is, which attraction is going to be stronger, the attraction towards the nitrogen nucleus or the attraction towards the hydrogen nucleus? Now, let me firstly just justify the statement that they will be feeling an attraction towards the nuclei of the nitrogen and the hydrogen atoms. Basically, electrons are negatively charged. Okay, the nuclei of the hydrogen and the nitrogen atom, these contain protons, which are positively charged. Okay, negative and positive charged particles attract one another, so these electrons will be being attracted towards the protons at the center of these two atoms, basically. Okay, right. So, if we're going to then answer the question of which of these two attractions is stronger, we need to consider firstly the number of protons in the two nuclei. Okay, now hydrogen only has one proton at its nucleus. Nitrogen has multiple. Okay, so that means that the actual positive charge in the nitrogen nucleus is stronger. So you might say, well then, of course, the attraction towards the nitrogen nucleus is going to be stronger than the attraction towards the hydrogen nucleus. But it's not quite that simple, because you also have to factor in the consideration that surrounding the nitrogen atom, you have more than just these two electrons, okay, and you'll have electrons that are closer to the nucleus than these two electrons, and those electrons that are surrounding the nitrogen nucleus, those will be shielding the positive charge of the nucleus from these two electrons, because those electrons that are orbiting around the nitrogen nucleus and are closer than these two electrons, those have a negative charge, and therefore they will be counterbalancing the positive charge of the nucleus. Whereas in the case of hydrogen, you don't have any other electrons shielding the proton at the center of the nucleus from these two electrons. Okay? So, basically, it's quite complicated to actually work out which of these two atoms is going to attract the electrons more. But we have a big word that means how good an atom is at pulling electrons within a covalent bond towards it. And this is electronegativity. Okay? So, the answer to this question is that nitrogen is better at pulling the electrons towards it than hydrogen. So these electrons do in fact sit towards the nitrogen and away from the hydrogen. Okay, we would say in this big word here, language, that nitrogen has a greater electronegativity than hydrogen, which means it's better at pulling electrons towards it than hydrogen is. Okay, right. So these two electrons in this single covalent bond here are going to sit towards the nitrogen atom, okay, and they're going to sit away from the hydrogen atom. Now, what does that mean? Well, it means that the nitrogen atom is going to get a partial negative charge, okay, because it has these electrons sitting slightly towards it, whereas the hydrogen atom is going to get a partial positive charge because it has lost these electrons partially. Okay, so this bond is going to become polar. It's got a negative pole, which is the nitrogen atom, and it's got the positively charged pole, which is the hydrogen atom. Now, in order to form a hydrogen bond, this is one of the requirements that you need. You need a partially positively charged hydrogen, such as the one that we've got here. Okay, so now let's put this bond back into the protein structure. This nitrogen will be partially negatively charged. This hydrogen will be partially positively charged here. Okay? Now, as I was saying, you need a partially positively charged hydrogen in order to form a hydrogen bond. And the partially positively charged hydrogen, because it has such a central role in the formation of hydrogen bonds, it's actually given a fancy name. Okay, it's known as the hydrogen, whoops, not like that. Okay, it's known as the hydrogen bond donor. Okay, right. Now, the other requirement to form a hydrogen bond is that you need what's known, oh dear, I'm not doing well today, hydrogen bond donor. The other requirement to form a hydrogen bond is that you need something called a hydrogen bond acceptor. Okay, so we now want to talk about what a hydrogen bond acceptor is. So basically, there are two requirements in order to be a hydrogen bond acceptor. Firstly, you have to have a partial negative charge so that you can interact with this hydrogen atom here, but also you need to have a lone pair of electrons. So basically, this carbonyl group, specifically this oxygen of the carbonyl group here, this is going to be our hydrogen bond acceptor. Okay, now let me discuss the properties that it has in a bit more detail now. Okay, so we'll start off with it being partially negatively charged. So let's pull this bond out here. We've got a carbon double bound to an oxygen, which is known as a carbonyl group. Okay, so this is a carbonyl group within our polypeptide. Okay, now we have a double bond here, so we have 4 electrons sitting in between this carbon and this oxygen. Now, oxygen actually has an extremely high electronegativity, higher than carbons basically. So the electrons in these two bonds here are going to sit towards the oxygen atom and away from the carbon atom. Okay, so the oxygen atom is going to get a partial negative charge here, shown here in red. Okay, whilst the carbon will end up with a partial positive charge. Okay, shown here in turquoise. Right, so that's one of the requirements you need to have in order to be a hydrogen bond acceptor. You need to have a partial negative charge. Okay, this is one of the things that's going to allow you to interact nicely with the hydrogen bond donor, which is this partially positively charged hydrogen. Okay, so this oxygen and this hydrogen can already interact nicely from what we've just discussed. But there is another requirement in order for this bond to actually be what's known as a hydrogen bond. Okay, and this is that the oxygen, or the hydrogen bond acceptor more generally, needs to have a lone pair of electrons. Now, oxygen actually has 2 lone pairs of electrons in this carbonyl group, but you only need 1. Okay, in order to form a hydrogen bond. So here in blue, this is a lone pair of electrons. Now, lone pairs of electrons are a center of negative charge. Okay, so what's going to happen basically is that we're going to have this oxygen here within this carbonyl group. This oxygen is going to have a partial negative charge, which means that it can interact nicely with the partial positive charge of the hydrogen. Moreover, it has this nice lone pair of electrons. The hydrogen atom will find this lone pair of electrons on this partially negatively charged oxygen, and it will form a very nice interaction there. Okay, a very strong electrostatic interaction, and this extremely strong electrostatic interaction which you form is known as a hydrogen bond. Okay, and usually hydrogen bonds are shown with dashed lines like so that I've put in there. Okay, right. I'll just sort of box it, so these dashed lines. So those are the bonds which actually hold polypeptides in alpha helices like so. Okay, so that's just a discussion of alpha helices. Now, that wasn't the bit that I actually wanted to discuss. There is a subtlety here that I want to stress because it's so important with what we're going to actually see in this video. Okay, which is that there are 2 different types of alpha helix. There is what's known as a left-handed alpha helix, and there is also what's known as a right-handed alpha helix. Now, the alpha helices that I've been drawing here and here, these are both right-handed alpha helices. Okay, well obviously they're both the same, what I've drawn here. But there is a different type of alpha helix, known as a left-handed alpha helix, and I want to explain the difference between a right-handed alpha helix and a left-handed alpha helix. Okay, so let's start with the right-handed alpha helix. What characteristic feature does a right-handed alpha helix have? Well, basically, you take your alpha helix, okay, and if it's a right-handed alpha helix, then if you work from the top to the bottom, okay, so you work your way around the alpha helix, going from the top to the bottom. You declare one side to be the top and one side to be the bottom. It doesn't matter whether this is the amino terminus or the carboxy terminus. Just call one side the top and one side the bottom. If you work from the top to the bottom, okay, and obviously you put the top in the normal position that a top would be in, okay, so you put it at the top. Okay, if you work from the top of your alpha helix to the bottom, which direction do you go round in as you loop? You go round in a clockwise direction. Okay, look, we are looping round. At the moment I'm at the back and I'm coming out to the front. Okay, now I'm looping round back to the back. I'm going round in a clockwise direction. Okay, so if you orientate your alpha helix so that you have a top and a bottom, one side is at the top and one side is at the bottom, okay, and you work your way from the top to the bottom, you go round in a clockwise direction, then your alpha helix is a right-handed alpha helix. Now, it does not matter whether you put this side at the top or this side at the top, okay, because if I now turn this upside down, Okay, so I've now made this side the top and this side the bottom. Then let's follow this round. How would it go? Well, at the moment I'm at the front, okay? Now I'm going round to the back, okay? Then I'm coming back out to the front, okay? And I agree it's a little bit weirdly drawn, but this is how it actually works. Okay, now I'm going back round to the back, then I'm coming out to the front, and you can see that I'm still going round in a clockwise direction.